What we're understanding now is that toward the end of their lives, stars start burning helium. And here's a diagram that shows the progression of the tracks of various mass stars and toward the end of their life. So we see the main sequence region, and up here is the point where it crosses the main sequence and enters into the phase of life where the hydrogen is done and the subsequent interesting processes take place that we're discussing. We tracked one solar mass star through the helium flash, and then we know it enters the horizontal giant branch after it reduces in luminosity, starts increasing in temperature. I also mentioned that this occurs for stars up to about 2 solar masses. After 2 solar masses, we no longer have a helium flash taking place. Why? Because there's enough mass so that the 100 million Kelvin temperature condition can occur without degeneracy happening. The core does not become degenerate before it reaches those temperatures. So a 3, 5, 9 higher mass stars will reach 100 million Kelvin and start fusing helium, and there are core changes that cause the star to reduce in luminosity, but not as significantly as what takes place in a helium flash. So higher than 2 solar mass, no helium flash. That's pretty important in the subsequent development of those higher mass stars. They all have some instability. So there's a region here of instability, especially with the higher mass stars, the lower mass stars also. But conditions in the helium core and also the helium in the atmosphere of the stars results in a pulsation in their luminosity, a change in luminosity where the star expands and then contracts again because of the amount of helium that's in its atmosphere. This is replicated over here in what's called the instability strip. Lower mass stars, for a period of instability, enter into what's called the RR Lyrae variable phase. The higher mass stars become, for a short period of time on their tracks, Cepheid variables. And those happen to be very important stars, a phase of a giant star that'll be useful to not only understand what's going on with the star, but also things like discovering distances in the galaxy and beyond, we've already alluded to. So the helium burning process is a little bit erratic, and many stars enter this short pulsation period that we want to investigate in a little more detail as well here. So the way that this works is that as the helium is produced and through compression is heated up to the point of ionization, that ionized helium in outer layers, and I keep saying the atmosphere of the stars, but really it's the helium that's in the layers of the star from the core out toward the surface. The ionized helium there makes the star opaque, and so heat is trapped. It's opaque to light, it's opaque to photons. The heat is trapped, expanding the star, cooling it, and after it cools, the helium recaptures the electron. The heat can escape and the cycle repeats. So here it is in graphic form. We have normal helium, 2 electrons. Well, as it's compressed and heated, it at least singly ionizes the helium, and so we have 1 electron. Well, it's now an ion that causes photons to be scattered, absorbed, irradiated, so it's essentially trapping the heat. So the heat is building up. When the heat builds up, the star expands, and when it expands, it cools. And as it cools, the helium can recapture the electron once again. Once that happens, the heat can escape. Namely, the photons can escape. And when it does that, it causes it to shrink back down, which starts the cycle all over again. And there turns out to be a relationship between the luminosity of this pulsating star and its pulsation period. That's a very interesting story in and of itself. But in a nutshell, the large stars, as shown here A large star pulsates very slowly. It's showing a 50-day period of the pulsation. Smaller stars, medium stars, pulsate more rapidly. A 10-day period, a small Cepheid variable is going to pulsate with a period of about 3 days. So there is this period luminosity relation that can be summarized simply as follows. The larger the star, the slower it pulsates. The smaller the star, the faster it pulsates. It's kind of intuitive when you think of a large object vibrating. Wop, 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 wop. It goes back and forth or in and out slowly, whereas think of a big, huge ball or something. A little tiny ball, you set it in vibration. It's vibrating very quickly. So turns out there is a specific relationship here, and I want to now show you a graph of that relationship with these Cepheid variables. This unit is on the birth and life of stars, so this instability region, this phase in the life of stars where it's a variable, a Cepheid variable in particular, is really important in its own right. But also, what's more significant in terms of practicality is the fact that these Cepheid variables can be used as a means of determining the distance to stars, which is very important for us to understand distances, to study the galaxy and beyond. So here is a graph of Cepheid variable curves. You'll notice that the luminosity is this way. It says absolute magnitude, which is the same idea. Over here is luminosity compared with that of the sun. So here's 100 times the luminosity of the sun, 1,000 times, 10,000 times. So these Cepheid variables are actually quite bright. And there's 3 different graphs. You notice it says type 1 and type 2 and then the RR Lyrae. So there are some varieties, and it's all based on the metallicity, the quantity of elements in the atmospheres in the various layers that is beyond hydrogen and helium. So that significantly affects their luminosity. I said that there's a period luminosity relation. Here's period. So for say a 10-day period, we could ascertain that a type 2 Cepheid has this luminosity, or if it's a type 1, it has this luminosity. Again, based on the constituents that make up that particular star. So type 1 and 2. Well, type 1 are the metal rich. So they have a lot of, significantly larger amount of heavy elements. They're population 1 stars, they're more luminous. Population 1 simply means that they're the population of stars that were first discovered. When you go outside and look up in the night sky, those stars are the ones that were first discovered, of course, and they are known as population 1. Then there's the metal poor population 2 stars. Those exist significantly in the bulge of the galaxy and in the globular clusters. They're older stars. The fact that they have less metals means that they are less luminous for a given period as well. So there's a lot of detail there, but that's the distinction in brief. The shorter period stars here in their own little category are known as the RR Lyrae variables. The name is based on where the first one was discovered in the constellation Lyrae. So knowing the absolute magnitude along with the apparent magnitude enables one to determine the distance to a star. Here is a classic formula of the magnitudes, the apparent and absolute, along with the distance. So if you can know the absolute magnitude of the Cepheid based on its period, you in fact can get that. You can always measure the apparent magnitude from Earth, and then you can discover the distance. So wonderful relationship there and very powerful in astronomy. I've already introduced you to how we can find the age of an infant star cluster by observing how the stars plot on the HR diagram and seeing which ones are entering the main sequence. Well, star clusters can also be used to discover the age of the cluster when it's older and discover the particular ages of older stars. So it's a good time to introduce clusters in brief. We have open clusters, which are on the arms of the galaxies. Here's a case in point, the Pleiades, very eye-catching open cluster. You can see with the naked eye. Always found in the disk of galaxies. That's important. We'll discuss that later. But they tend to be young in age. And this is the Pleiades, spectral type B. So B stars means they're bright, young stars. If they were old, there would be no B-type stars in the cluster. Usually several thousand stars. In the case of the Pleiades, it's at least about a half a thousand. They're not gravitationally bound. Over time, they disperse. So they formed approximately in place, and then the tug from other parts of the galaxy disperses them. Then we have the globular clusters. You notice right away there's a significant difference in the look of that cluster. M80, they're found in the halo of the galaxy. These are stars in a different region of the galaxy. They're the oldest stars in the universe and can have more than 1 million stars in the cluster itself. And even the center region, small center region, a few light years across, contain thousands of stars. Down at the bottom here, what I'm going to show you is the spectra of stars. In the top part, we have metal poor or population 2 stars that we just discussed. Those would be found in the clusters. And then in the bottom part, we have the spectra of the metal rich population 1 stars, like we have with the open clusters. And you'll in fact notice a significant difference between these two, that the color of a globular is a lot more reddish because all the bright blue stars have subsequently burnt out. And so there is mainly the red dwarfs and the giant stars left in the globular clusters. But notice the absorption lines here. So we have hydrogen absorption lines in both types of stars, but only in the metal-rich stars we see all these other significant absorption lines in the spectrum because of all the other elements that are in the stars. And that has a lot to do with the Cepheid variable details, the luminosity of the stars for a given mass. If we plot a star cluster, like in this case the Pleiades on an HR diagram, we can obtain the age of the cluster. Now, it's not an infant cluster, but it's relatively young. And we're not doing what we did before, which is looking to see which stars have just entered the main sequence. It's kind of the opposite. We're looking to see which stars are leaving the main sequence and dying off. Well, what we'll notice when we plot the Pleiades stars, we'll notice that there are no O-type main sequence stars. The O-type stars have all left the main sequence. The cluster is old enough that those stars are already burned out. So what we do is discover that actually spectral type B6 stars are just turning off. Here's what's called the main sequence turnoff point. The stars that are just leaving the main sequence, they happen to be spectral type B6. And so we know how old B6 type stars can be before they deplete their hydrogen and leave the main sequence. And as such, the age of the cluster is determined to be about 100 million years. It's a wonderful technique. Therefore, we know the age of the stars in that whole cluster. So this can be done with many clusters. Here's showing essentially the same thing with a variety of clusters. Several open clusters, not showing all the stars. The red dwarfs are not providing any additional information for us. But in each case, the age of the cluster is equal to the lifetimes of the stars that are turning off, that are at the main sequence turnoff point. So here's the listing of those various ages. So if it's O-type stars that are leaving, that's a really young star cluster. But if they're turning off way down here, then all these stars, these high mass but increasingly lower mass stars, have already turned off, and that indicates a much older cluster, and therefore all the stars are older as well. So we've discovered using this technique that the open clusters are in general less than 5 billion years in age, while the globular clusters are older than 10 billion years. And let's just look at a globular cluster now also and see how it looks on an HR diagram. The age of a globular cluster can be found in the same way. Here we have globular M4. We see the main sequence turnoff point is just about where our star, the Sun, is. That would indicate approximately that the cluster is about 10 billion years old, but there's complexities to everything, and it turns out that it really is consistent with the age being about 13 billion years old, which, by the way, constrains the age of the universe. Back in the 90s, there was some tension here. It looked like some globular clusters had stars that were older than the measured age of the universe, but that's subsequently come into alignment, as of course it must somehow. The universe is about 14 billion years old, and this is consistent with the oldest globular clusters as well. Certain binary stars can be significantly modified in their evolutionary tracks as a result of mass transfer from one to the other. Now, to set this up, there's a similar idea associated with placing spacecraft at certain locations in orbit so that we can study features of the universe. In this particular case, we're talking about the WMAP, which is investigating the first echoes of radiation coming from shortly after the Big Bang. The origins of the universe. Basically, what we have is a location here of stable orbit where at this mathematical point, it's called the Lagrange L2 point, the gravitational tug of Earth and the Sun together caused this spacecraft to orbit with the Earth, always in opposition because of the enhanced gravitational tug. Diminished here at L1 so that even though it's in a smaller orbit, it tracks with the Earth also. So it's always basically orbiting in the same orbital period as Earth does. Well, how does this relate to binary systems? Well, the same mathematics is applied. And what you have is a mathematical region called the Roche lobes that define the area, the volume of space over which a particular star has gravitational control. So L1 is the point that's interesting. If this larger star if it goes into red giant phase, it fills its Roche lobe with gas. If it continues to expand, that gas will bleed over through L1 and be accreted onto the smaller star. So the smaller star will grab some of that mass and gain mass in the process, thus significantly changing the course of its development. So this is going to be exceptionally important as we study binary systems pertaining to supernova, neutron stars, black holes, where the actual development of these objects is mediated by this mass transfer process. This sequence of graphics kind of shows the various possibilities for the binary systems and these Roche lobes. So here we have a small star and the larger star. This is a detached binary. These stars are not in contact with each other, but this still defines the mathematical region of their gravitational control. Semi-detached binary over here, this star has blown up and filled its Roche lobes, and now some of its matter can transfer over to the smaller one. A contact binary is just simply where both lobes are filled and they're just in contact. That's a very rare situation where it just meets that criteria uniquely. More typically, it would be overflowing and over contact, where the atmospheres are literally touching each other, and so they're orbiting each other while their atmospheres are in contact. So those are some of the possibilities with these various configurations. So as an example of this mass transfer process, we have what's known as the Algol paradox. It's an eclipsing binary as we see it today. This is Algol in the constellation Perseus. Well, we start with a higher mass and lower mass star. This is the initial condition of these stars. And as we know, the higher mass star goes through its nuclear fusion, hydrogen fusion faster and gets toward the end of its life and then blows up to become a red giant, which we see in the second picture. And we have mass transfer taking place when it fills its roach lobe. And the smaller companion starts accreting that matter, gaining some of the mass that was originally from the higher mass star. So its mass progressively increases. And then what we see is over a period of time, this is what it looks like today. The red giant has become a subgiant. Notice the roach lobe is smaller. It's gone down to 0.8 solar masses. And what was the smaller star has gained so much mass that it's 3.7 solar masses. You may recognize the paradox, namely that how can a 3.7 solar mass star be a main sequence star as a companion to a 0.8 solar mass red giant? So the 0.8 solar mass should not become a red giant until much, much later than a 3.7 solar mass star. So we see that the paradox is resolved when we recognize the extremely large amount of change that takes place with these stars as a result of the transfer of mass from one to the other. This will become very important when we study the death of stars, which is black holes, white dwarfs, and neutron stars, and how they are affected by mass transfers in binary systems. In the final slide, we just list main sequence stars of the various spectral types, O through M. We see the variation in mass, how the mass goes down. You go from O toward M. And in much greater proportion, the luminosity is going down from 405,000 to 0.08 in terms of the luminosity of the sun. Far more significant change there than in the mass. And then the years as well. The years from 1 million on up to 56 billion. So it gives you just an idea of the ranges of mass, luminosity, and ages of stars on the main sequence. And this will conclude our basic introduction of the birth and life of stars, and we're now going to move on to the study of the actual deaths of stars and the objects and processes that occur with the final gasps of these poor stars.